And now, in this lecture, we will find the radius of the small circle. In the drawing, we have a square, and we know that side AB, or one side of this square, is equal to 8 units. So AB equals to AD equals to BC equals to DC equals to 8 units. And inside this square, we have two circles. The radius of this small circle is equal to R. The radius of this big circle equals to 2R. And we want to find out the radius of this small circle, or the size of the radius of this small circle. Okay? So, first of all, we will define the center of the small circle as point P, and the center of the big circle as point Q, and we will join together points A and P by a straight line. And we'll draw radius from the center of this small circle to this point of tangency. We'll define this point of tangency as point N, or the touching point between the tangent A. This point will be defined as point E. So the touching point between the tangent AE to the small circle will be defined as point N. And we will draw, so this is the radius of the small circle. It will be equal to R. And we will draw the second radius from the center of this circle, that is to say from point P to the tangent to the point that AB is tangent to this small circle, and we will define the touching point between tangent AB to the small circle as point M. And actually we have a rule. We'll call it rule number 1. Rule number 1 states that a tangent to a circle is perpendicular to the radius perpendicular to the radius drawn to its point of tangency. To its point of tangency. I read rule number 1 again. A tangent to a circle is perpendicular to the radius drawn to its point of tangency. So actually the meaning of rule number 1 is that if you have a circle and let's define this center of the circle as point A, and we draw here the radius of this circle, and we have tangent to this circle at this point. Let's define this point B, and we will define the tangent as CD. Then, according to rule number 1, the tangent CD to this circle, that is tangent to this circle at point B, is perpendicular to the radius drawn to its point of tangency. So actually the point of tangency is point B, and we have this radius that is drawn to the point of tangency, that is to say point B. Therefore, according to rule number 1, the tangent CD is perpendicular to this radius that is drawn to its points of tangency, that is to say to point B. So this tangent CD is perpendicular to the radius at the point of tangency. And the point of tangency is point B. Therefore, at point B, the tangent is perpendicular to this radius that is actually drawn to its point of tangency. So this angle is 90 degrees, and this angle is also equals to 90 degrees. So as you can see from the drawing, the radius AB, or the radius R, is drawn to the point of tangency, that is to say to point B. Therefore, the tangent CD is perpendicular to this radius that is drawn to the point of tangency, that is to say to point B. That is to say, this angle is 90 degrees and this angle is 90 degrees. The tangent CD is perpendicular to this radius that is drawn to the point of tangency to point B. So this angle is 90 degrees and this angle is also 90 degrees. Okay? And So actually, according to rule number 1, this tangent AB, that is tangent to the small circle at point M, will be perpendicular to this radius that is drawn to the point of tangency, that is to say, point M. Again, the tangent AB is perpendicular to this radius that is drawn to the point of tangency, that is to say, to point M. So this angle is equal to 90 degrees because of the fact that the tangent AB is perpendicular to this radius at the point of tangency, that is to say, at point M. So at point M, the tangent AB is perpendicular to this radius, that is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And the same thing is true, is also at this point M, point N. This point N is point of tangency of the tangent AE. So we have this radius that is drawn to the point of tangency point N. Therefore, this angle is a right angle. It equals to 90 degrees. And this angle is also a right angle that equals to 90 degrees. And the same thing is true at this point. Actually, the tangent AD is tangent to this circle at point, let's say, S. So the tangent AD to this circle is perpendicular to this radius that is drawn to the point of tangency, that is to say, to point S. So at point S, the tangent is perpendicular to this radius. This is to say, this angle is a right angle. It equals to 90 degrees. And this angle also a right angle that equals to 90 degrees. Okay? And we also have rule number 2. Rule number 2 states that if from one external point two tangents to a circle, two tangents to a circle are drawn, then they have equal lengths. So I will read rule number 2 again. Rule number 2 states that if from one external point two tangents of a circle are drawn, then they have equal lengths. Okay, so actually the meaning of rule number 2 is that if you have a circle and from external point to this circle, that is to say from point, for example, P, that is external point to this circle, you draw two tangents to this circle. This is the first tangent. Let's define the touching point between the tangent to this circle as point A, and you draw also a second tangent to this circle, and let's define the touching point between this circle to the tangent to this circle as point B. So according to rule number 2, the lengths of these two tangents that exist from the same external point, that is to say from point P, are equal. So that is to say AP equals to BP. Okay, so if you draw two tangents from external point of a circle, that is to say from point P to this circle, then the lengths of those two tangents are equal. That is to say AP equals to BP. Okay, so actually we can implement rule number 2 in our drawing. If we focus on the right triangle AMP, this right triangle, and the right triangle, this right triangle ANP, we actually will prove that those two right triangles can go into each other. Again, we'll prove that the right triangle AMP can go into the right triangle ANP. First of all, AM equals to AN. AM equals to AN. According to rule number 2, again, AM equals to AN according to rule number 2, because we have here external point A, this external point to this small circle, and from the external point A, we have two tangents to the small circle. The first tangent is AM and the second tangent is AN. Therefore, according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, AM equals to AN. So AM equals to AN according to rule number 2. And we have here MP that equals to PN, that equals to the radius of the small circle. MP equals to Pn, that equals to the radius of this circle. Okay, and we also have here a common side. AB is a common side, it belongs to both triangles, so we can write down that AP equals to AP is a common side that belongs to both triangles AP equals to AP is a common side that belongs to both right triangles. So AP equals to AP is a common side that belongs to both triangles. So we actually proved that three sides of the right triangle AP are corresponding equal to the three sides of the right triangle ANP. Therefore, we proved that triangle AMP is congruent to triangle ANP according to side rule. I'll write it down. The right triangle AMP is congruent to the right triangle ANP according to side rule. I will repeat again. The right triangle ANP is congruent to the right triangle ANP according to side rule. So what is side rule? Side rule is that if you prove that three sides of one triangle are corresponding equal to three sides of another triangle, then you prove that those two triangles can go into each other according to side rule. Okay, so those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Okay? So actually angle MAP, this angle, is equal to angle NAP, this angle. Again, angle MAP equals to angle NAP according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles will be equal to each other. And if we define this angle as alpha, then this angle will be also equal to alpha because of the fact that they are equal to each other. So we actually found out that angle MAP equals to angle NAP, and both angles are equal to alpha according to our definition. Okay, so in the next step we will join together points A and Q by a straight line. And we will draw radius of this big circle from the center of the circle, that is to say from point Q to the touching point of the big circle with the tangent AN. Okay? We define the touching point between tangent AN and this circle as point L. Okay? So according to rule number 1, those two angles are right angles, they are equal to 90 degrees because of the fact that the tangent AN is perpendicular to the radius of the big circle. This radius at the point of tangency, that is to say at point N, so this angle is 90 degrees and this angle equals also to 90 degrees. And in the next step, we will prove that those two right angles can go into each other. Okay, so we will prove that triangle ALQ, the right triangle ALQ, and is congruent to the right triangle ASQ. Okay. I will repeat again. We will prove that the right triangle ALQ can, the right triangle ALQ congruent to the right triangle ASQ. First of all, we have here two radiuses of the big circle. They are of course equal to each other, so SQ equals to QL, SQ equals to QL, and both those two radiuses of the big circle are equal to 2R. Okay? SQ equals to QL, and both those two radiuses of the big circle equals to 2R. And also AS equals to AL, AS equals to AL, and actually they are equal to each other according to rule number 2, because from this external point A we have two tangents to this big circle, tangent AS and tangent AL. According to rule number 2, the lengths of two tangents from external point of a circle, that is to say from point A, are equal. So AS equals to AL according to rule number 2. Again, AS equals to AL according to rule number 2. And we have here a common side AQ, or QA is a common side. It belongs to both right triangles, so we can write down that QA equals to QA. It's a common side that belongs to both right triangles. So we proved QA equals to QA, it's a common side, so we actually prove that the three sides of the right triangle ALQ are correspondingly equal to the three sides of the triangle ASQ. Therefore, we proved that those two triangles can go into each other according to side rule. So I write it down. Triangle ALQ congruent to triangle ASQ according to side rule. So I'll repeat again, the right triangle ALQ congruent, this is the sign of congruent, to the right triangle ASQ according to side rule. We actually proved that all the three sides of the right triangle ASQ are correspondingly equal to all the three sides of the right triangle ALQ. Therefore, we proved that those two triangles can go into each other according to side rule. From the fact that those two right triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles, these two corresponding angles will be also equal to each other. So we write down that angle LAQ is equal to angle SAQ. Okay, angle LAQ equals to angle SAQ according to the rule that corresponding angles in congruent triangles are equal to each other. And if we define this angle as beta, then this angle will be also equal to beta because of the fact that they are equal to each other. So we actually found out that angle LAQ is equal to angle SAQ, and both angles are equal to beta according to our definition. Okay? But we also know that all the angles of a square are equal to 90 units. They are right angles, and especially angle DAB of square ABCD is a right angle, it equals to 90 degrees. So we will write down that angle DAB equals to 90 degrees. It is a right angle. So angle DAB equals to 90 degrees because of the fact that all the angles of a square are right angles, they are equal to 90 degrees, so all the angles of the square ABCD are equal to 90 degrees. But we know that angle DAB consists of four angles, alpha, alpha, and beta. So we can write down that angle DAB that equals to 90 degrees, it is actually equals to 2 alpha plus 2 beta. Okay? We will divide this equality by 2, and we will get that alpha plus beta equals to 45 degrees. But if alpha plus beta equals to 45 degrees, then tangents alpha plus beta will be equal to tangents 45 degrees. Very simple. So tangents alpha plus beta will be equal to tangents 45 degrees. And we know that tangents 45 degrees equals to 1. So we got that tangents alpha plus beta equals to 1. But we also have a trigonometric identity from tangents alpha plus beta. The trigonometric identity for tangents alpha plus beta, it is actually tangents alpha plus beta equals to tangents alpha plus tangents beta over 1 minus tangents alpha times tangents beta. Okay? So actually we can substitute tangents alpha plus beta in this equality by this expression. So we'll do it now. instead of tangents alpha plus beta, we will write that tangents alpha plus tangents beta over 1 minus tangents alpha times tangents beta equals to 1 according to this trigonometric identity. We define it as equation 1. So actually, according to this trigonometric identity, or according to this trigonometric identity, tangents alpha plus beta equals to this expression. So this expression will be equal to 1. And we will get that tangents alpha plus tangents beta over 1 minus tangents alpha times tangents beta will be equal to 1. Again, we actually substituted tangents alpha plus beta in this equality by this expression because of the fact that tangents alpha plus beta equals to this expression. And we got that tangents alpha plus tangents beta over 1 minus tangents alpha times tangents beta equals to 1. Okay? So we will find out the value of tangents alpha and tangents beta from the drawing. So here we know that AMP or PMA is a right angle, and actually we also know that all the angles of a square, all the angles of a square are right angles, they are equal to 90 degrees. So angle ABC, this angle is a right angle because it is one of the square angles. It is one of the square ABCD angles, therefore it equals to 90 degrees. According to rule number 1, if we define the touching point between the tangent CB to the small circle as point Z, then we know that the tangent BC, that is tangent to the small circle at point Z, will be perpendicular to this radius according to rule number 1 that states that a tangent to a circle is perpendicular to the radius at the point of tangency. So this radius is drawn to the point of tangency, that is to say point Z, therefore the tangent BC will be perpendicular to this radius at the point of tangency, that is to say it's point Z. So at point Z we will have here 90 degrees with this radius, that is to say this angle is 90 degrees and this angle is also 90 degrees. So if we look at quadrilateral PZMB, at quadrilateral PZMB, this quadrilateral PZMB, we have 3 right angles, 1, 2, and 3, and the sum of 3 right angles is actually 270 degrees. Okay, the sum of the 3 right angles is equal to 270 degrees. And we also have the rule that states that the sum of the angles in any quadrilateral equals to 360 degrees. So the sum of the angles in quadrilateral PZMB equals to 360 degrees. Okay? So the sum of the angles in quadrilateral PZMB equals to 360 degrees. So in order to complete the sum of the angles in this quadrilateral to 360 degrees, the size of the fourth angle must be equal to 360 degrees minus 270 degrees, that is actually 90 degrees. So we actually found out that the size of angle MPZ equals to 90 degrees, that is to say, it is a right angle, it equals to 90 degrees. So here in quadrilateral PZMB, we have four right angles. And any quadrilateral that has four right angles must be at least rectangle. If not a square, any quadrilateral that has four right angles must be a rectangle. Okay, so quadrilateral PZMB is at least rectangle. Okay, so I write it down that quadrilateral PZMB that has four right angles must be at least a rectangle. I repeat again, this quadrilateral PZMB that has four right angles, it must be at least rectangle. But we know that the opposite sides of any rectangle are equal to each other. The opposite sides of a rectangle are equal to each other. That is to say, MP equals to ZB. MP or PM equals to ZB. Okay? And PM equals to R, so ZB that equals to PM must be also equal to R. And also the two opposite sides PZ and MB must be equal to each other in the rectangle PZMB. So PZ equals to MB. But we know that PZ equals to R, so MB must be also equal to R. Okay? And we also know that AB equals to 8 units. Actually, AB equals to BC equals to AD equals to DC equals to 8 units, because all the sides of a square are equal to each other. So AB equals to 8 units and MB equals to R. So the size of AM will be equal to AB minus AM. AB is 8 units and MB is R. So the size of AM will be equal to 8 units, that is AB, minus MB, that is R. That is to say, AM equals to 8 minus R. Okay? So the value of tangent alpha is the relationship between the side that is in front of angle alpha divided by the side that is near angle alpha. That is to say, tangent alpha equals to PM over AM. Okay, I'll write it down. Tangent alpha equals to PM over AM. Again, tangent alpha equals to PM over AM. But what is the value of PM? PM equals to R. And what is the value of AM? AM equals to 8 minus R. So in total we found out that the value of tangent alpha is actually R over 8 minus R. Let me repeat again, the value of tangent alpha is actually R minus 8 minus R, because PM equals to R and AM equals to 8 minus R, so the value of tangent alpha is R over 8 minus R. Okay, so we will draw the radius of the big circle from the center of the big circle, that is to say from point Q to the touching point between the tangent DC to the big circle. Okay, we will define the touching point between the tangent DC to this big circle as point G. Okay. First of all, we know that all the sides, all the angles of a square are right angles, so angle ADC will be equal to 90 degrees, that is to say it is a right angle. And according to rule number 1, this is the radius of the big circle, it equals to 2R because it exits from the center of the circle and touches the circle at point G, so QG is defined as the radius of the big circle, that is to say it equals to 2G. And we have rule number 1, that the tangent DC to the big circle is perpendicular to this radius that is drawn to the point of tangency, and the point of tangency is point G. So the tangent DC is perpendicular to this radius at the point of tangency, so that is to say that this angle equals to 90 degrees and this angle also equals to 90 degrees because the tangent DC is perpendicular to this radius at the point of tangency. It is perpendicular to this radius at point G, that is to say this angle is 90 degrees and this angle is 90 degrees. And we repeat on the same process as we did in this small square. We repeat on the same process as we did in the small square PZMB. We have here bigger square, so we will actually prove that the quadrilateral QSGD is a square. So first of all, we know that the three angles, the sum of the three angles of quadrilateral SQGD is equal to 270 degrees because the sum of three angles that each of them is equal to 90 degrees is 270 degrees. And as we did in this quadrilateral, the third angle must be equal to 90 degrees in order to complete the sum of the angles in quadrilateral QGDS to 360 degrees. That is to say, here we have three angles that the sum of them is 270 degrees. So the third angle must be equal also to 90 degrees in order to complete the sum of the angles in quadrilateral ADSQ to 360 degrees, because here 270 degrees plus 90 degrees will be equal to 360 degrees. So we actually found out that quadrilateral DGQS has four right angles, and any quadrilateral that has four right angles, it must be at least rectangle. Okay, so we know that according to the rule that any quadrilateral that has four right angles, it must be at least rectangle, that quadrilateral QSGD, the quadrilateral QSGD is at least a rectangle. Again, quadrilateral QSGD is at least a rectangle because it has three right angles, and any quadrilateral that has three right angles is at least a rectangle. And we also have the rule that states that the opposite sides of a rectangle are equal to each other. That is to say, QG equals to SD. QG equals to SD because the opposite sides of the rectangle QGSD are equal to each other. So QG equals to SD. But QG equals to 2R. It is the radius of the big circle. So SD will be equal also to 2R, and SQ equals to GD because the opposite sides of the rectangle are equal to each other. But we know that SQ equals to 2R, so GD will be also equal to 2R. So here we have rectangle that has four sides that are equal to each other. So actually the rectangle QSGD is actually a square, because any shape that has four right angles and also four sides that are equal to each other, it is actually a square. So the shape QSGD is a square. Okay? So we actually know that SD equals to 2R, and AD is one side of a square ABCD. Okay, AD is one side of square ABCD, and we know that all the sides of square ABCD, they are all equal to 8 units. So AD equals to 8 units. Therefore, AS will be equal to AD minus ASD. Again, AS will be equal to AD minus SD. That is to say, AS equals to AD, that is 8 units, minus SD, that is 2R. Again, AS equals to AD, that is actually 8 units, minus SD, that is 2R. So SD equals to 8 minus 2R. Again, AS equals to AS equals to 8 minus 2R. Okay? So what is the value of tangents beta? tangent beta equals to the relationship between the side that is in front of angle beta, that is to say SQ, over the side that is near angle beta, that is to say AS or SA. Okay, so tangent beta equals to SQ over SA. But we know that SQ equals to 2R and SA equals to 8 minus 2R. Okay, so in total we got that the value of tangent beta, it is actually 2R over 8 minus 2R. This is the value of tangent beta, and we have already found out that tangent alpha equals to R over 8 minus R. Okay, so after we found out the values of tangent alpha and tangent beta, we actually can substitute tangent alpha and tangent beta in this equation number 1 by the values that we found for tangent alpha and tangent beta. Okay, so we'll do it now. We substitute tangent alpha and tangent beta by the values that we found for tangent alpha and tangent beta. So in equation number 1, instead of tangent alpha, we will write down the value for tangent alpha, that is actually R over 8 minus R, and the value of tangent beta, according to what we have already found out, that is actually 2R over 8 minus 2R. And all divided by 1 minus tangent alpha times tangent beta, that is to say R minus 8 minus R times tangent beta is 2R over 8 minus 2R, all equals to 1. So actually we substituted the values of tangent alpha and tangent beta in this equation number 1 by the values that we found for tangent alpha and tangent beta, and we got this expression. So here we have one equation with one variable that is missing. So we will do a common factor for these two expressions, and we will get that the common factor for those two expressions will be 8 minus R times 8 minus 2R, and here we will have R times 8 minus 2R plus, here we have 2R times 8 minus r. So as you can see, this expression is exactly equal to these expressions in the numerator, and then we will divide it by 1 minus this expression. All equals to 1. Here we will substitute 1 by 8 minus r over 8 minus r times 8 minus 2r over 8 minus 2r, in order to have a common factor with this expression. Okay? We get that r times 8 minus 2r plus 2r times 8 minus r over 8 minus r times 8 minus 2r, all divided, and we'll substitute 1 by the expression of 8 minus r over 8 minus r times 8 minus 2r over 8 minus 2r. Okay? So we actually substituted 1 by this expression. As you can see, this expression equals to 1 because it is 8 minus r over 8 minus r, 8 minus 2r over 8 minus 2r, so this expression equals to 1. So, and we have also minus this expression that is actually 2r squared. Okay, it is actually minus 2r squared, all equals to 1. Okay? So here we have 2 minus r times 2 minus 2r in the denominator, and we have 2 minus r times 2 minus 2r, exactly the same expression in the denominator. So this expression will get cancelled because when we divide those two equal expressions one by each other, it will be equal to 1. So those two expressions will get cancelled, and we only left with those. This will be the numerator and this will be the denominator after we cancelled those two expressions. We get that r times 8 minus 2r times plus 2r times 8 minus r over this expression 8 minus r times 8 minus 2r minus 2r squared, all equals to 1. Okay? So we will open the brackets in this expression. and we will get that r times 8 is 8r minus r times minus 2r is minus 2r squared plus 2r times 8 is 16r and 2r minus r is minus 2r squared, all divided by 8 times 8 is 64, 8 times minus 2r is minus 16r, minus r times 8 is minus 8r, and minus r times minus 2r is plus 2r squared minus 2r squared. Actually 2r squared minus 2r squared is 0, so 2r squared minus 2r squared equals to 0, so it will get cancelled, and what is left after and all equals to 1, of course. So what is left after we cancel these two expressions is actually, here we have 2r plus 16r is 24r, and we have here 2 minus 2r squared minus 2r squared is minus 4r squared. Okay, so and it is divided by 64 minus 16r minus 8r all equals to 1. So we got this expression. Here we will cross multiply this expression. Okay, we will get that 24r minus 4r squared equals to 64 minus 16r minus 8r. Okay, minus 8r. So we have here 24r minus 4r squared equals to 64 minus 16r minus 8r is minus 24r. So here we'll subtract from this equality 24r, and we'll get that minus 4r squared equals to minus 48r plus 64. Here we will add to this equality 4r squared, and we will get that 4r squared minus 48r plus 64 equals to 0. So here we have a quadratic equation. We will divide this quadratic equation by 4, and we will get that r squared minus 48 over 4 is minus 12 r plus 64 over 4 is 16. So we actually got this quadratic equation, and we know that the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. This is the general formula for a quadratic equation when a, b, and c are the coefficients of a quadratic equation and x is the variable that we are looking for. And the solution for this quadratic equation, or the way to find out the variable x that we are looking for, we have a special formula that we will use in order to find out the value of x in this general quadratic equation. And the special formula for x is x equals to minus b plus minus root of b squared minus 4 times a times c over 2a, when a, b, and c are the coefficients of this quadratic equation and x is the variable that we are looking for. And in our specific quadratic equation, the variable that we are looking for is r, so x equals to r. X equals to r, and the coefficients a, b, and c, actually a equals to 1, b equals to minus 12, and c equals to 16. So we will use this formula in order to find out the value of x that is actually r. So x equals to r, so r equals to minus b, b equals to minus 12, so minus b is minus minus 12, minus minus 12 is 12, plus minus the root of b squared, b equals to minus 12, so b squared will be equal to minus 12 squared, minus 12 squared is 144, minus 4 times a times c. Minus 4 times a is 1, so minus 4 times 1 is minus 4, and minus 4 times 16 is minus 64, over 2 times a, 2 times a is 1, so 2 times 1 is 2, so r equals to 12 plus minus 100, in the root we have 144 minus 64, 144 minus 64 is 80, so in the root we have only 80 over 2. So we got that r equals to 12 plus minus root 80 over 2. Okay? And r equals to 12 plus minus, we know that 80 is 4 times 20. 80 equals to 4 times 20, so we write it down over 2. Okay, so we got that r equals to 12 plus minus 40 times 20, that is actually 80. The root of 4 is 2, so I write it down. And the square root of 4 is 2, so r equals to 12 plus minus the square root of 4 is 2 times root 20 over 2. So r equals to 12 over 2 is 6, plus minus 2 over 2 is 1, so it is root 20. Actually, 20 equals to 4 times 5, so we'll write it down that r equals to 6 plus minus the root of 4 times 5. And again, the root of 4, the square root of 4 is 2, so we'll get that r equals to 6 plus minus 2 times root 5. So we have here 2 roots for r, or 2 answers for r. The first solution is that r equals to 6 plus 2 times root 5, and the second solution is that r equals to 6 minus 2 times 2 times root 5. Okay? But we know that the size of one side of square ABCD is 8 units. AB equals to 8 units according to what is given us in the question. AB equals to 8 units. All the sides of the square ABCD are equal to 8 units, so AB equals to 8 units, and so actually here, and you can see from the drawing that the small circle is inside the square. Also, actually both circles are inside the square ABCD, especially the small circle is inside square ABCD. Because of the fact that the small circle is inside the square ABCD, the radius r must be less than 8 units. Okay, so r is less than 8 units, r is less than 8. So the answer that r equals to 6 plus 2 times root 5, that is actually greater than 8 units, it is not correct, because the radius of the small circle must be less than 8 units. Okay, so the only answer that is left is that the radius of the small circle, that is to say r, will be equal to 6 minus 2 times root 5. That is about 1.53 units. Okay, that is the answer to the question, that the radius of the small circle equals to 6 minus 2 times root 5, that is about 1.53 units. Okay, I will repeat again. The radius of this small circle, equals to 6 minus 2 times root 5. The radius of this small circle equals to 6 minus 2 times root 5, that is about 1.53 units. Okay, so now I'll summarize the lecture. Actually, we wanted to find out the radius of this small circle, and we have square ABCD, that the side of one side of square ABCD equals to 8 units, and inside this square ABCD we have two circles. We have the big circle that is inside the square, and the radius of the big circle equals to 2 times r, and the radius of the small circle equals to r. And we want to find out the value of r. Okay, so actually, in order to find out the value of r, we did subtractions. We defined the center of the small circle as point P and the center of the big circle as point Q, and we actually join together points A and P by a straight line, and we draw from point P radius to the touching point between the tangent AB to the small circle, that is to say to point M, and we draw another radius from the center of the circle to the touching point between the tangent AE to the circle, that is to say to point N. So Pn is the second radius, and we actually proved that those two right triangles can go into each other. We actually have rule number 1 that states that a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So this tangent CD to this circle, that is CD is tangent, or the tangent CD is tangent to this circle at point B. So point B is the point of tangency, and according to rule number 1, a tangent to the circle, that is to say CD, is tangent to this radius at the point that is drawn to the point of tangency. This radius is drawn to the point of tangency, that is to say point B. So the tangent CD is perpendicular to this radius, and that is drawn to the point of tangency, that is to say point B. So the tangent CD is perpendicular to this radius at point B, that is to say this angle is 90 degrees and this angle is 90 degrees. So when you have tangent to a circle and the radius that is drawn to the point of tangency, that is to say to point B, then the tangent will be perpendicular to this radius, that is to say this angle is 90 degrees and this angle is 90 degrees. Okay? And we also have rule number 2. Rule number 2 states that if from one external point two tangents to a circle are drawn, then they have equal lengths. So here we have this circle, and from external point to this circle, that is to say from point P, we drew two tangents to this circle, tangent PA and tangent PB. Then according to rule number 2, the lengths of those two tangents are equal to each other. That is to say AP equals to PB or BP. Okay, so if from external point you draw two tangents to a circle, then the length of those two tangents will be equal to each other. That is to say AP equals to BP. Okay, and we proved that those two right triangles, triangle ANP and triangle AMP, are congruent to each other. First of all, AM equals to AN. Again, AM equals to AN. According to rule number 2, that the tangent that you draw from external point to a circle are equal to each other. So we have from point A, we have two tangents to the small circle, tangent AM and tangent AN. According to rule number 2, the lengths of those two tangents are equal to each other, that is to say AM equals to AN. So actually AM equals to AN according to rule number 2, and MP equals to NP. Both of those two sides are the radiuses of the small circle, so they are equal to each other. AM equals to MP equals to PN equals to the radius of the small circle, and we have also a common side. AP is a common side, it belongs to both triangles, so AP equals to AP is a common side. So we proved that triangle AMP is congruent to triangle ANP according to side rule. Okay? And from the fact that those two triangles can go into each other, we will conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles will be also equal to each other. So if this angle is alpha, this angle will be also equal to alpha because of the fact that those two angles are equal to each other. So angle MAP equals to angle NAP, and both angles are equal to alpha according to our definition. Then we actually proved that those two triangles can go into each other according to the same rule, according to side rule. We actually know that AN equals to AS, AN equals to AS equals to AN, AS equals to AN according to rule number 2, and QL equals to SQ. Both those two line segments are the radiuses of the big circle, therefore they are equal to each other, and AQ is a common side, it belongs to both triangles, therefore AQ equals to AQ is a common side. So triangle ALQ can go into triangle ASQ according to side rule, and we can conclude from the fact that those two right triangles can go into each other, that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. And if this angle is beta, then this angle will be also equal to beta because of the fact that those two angles are equal to each other. So if this angle is beta, this angle is also beta. Then you know that all the angles in a square are right angles, they are equal to 90 degrees, therefore angle DAB, this angle, that is one of the angles of triangle ABCD, will be equal to 90 degrees. So angle DAB equals to 90 degrees. But angle DAB consists of 4 angles, so beta plus alpha will be equal to 90 degrees, that is to say 2 alpha plus 2 beta equals to 90 degrees. We divided this equality by 2, and we got that alpha plus beta equals to 45 degrees. If alpha plus beta equals to 45 degrees, then tangent alpha plus beta will be equal to tangent 45 degrees. Tangent 45 degrees is 1. So we got that tangent alpha plus beta equals to 1, and we have trigonometric identity for tangent alpha plus beta. Tangent alpha plus beta equals to tangent alpha plus tangent beta over 1 over tangent alpha times tangent beta. So we will substitute tangent alpha plus beta by this expression that equals to tangent alpha plus beta, and we will get that tangent alpha plus beta equals to this expression, and this expression equals to 1. And actually tangent alpha equals to PM over AM, so it equals to R over 8 minus R. Tangent alpha equals to R over 8 minus R, and tangent beta, according, if you look in this right triangle, tangent beta equals to SQ over AS. SQ equals to 2R and AS equals to 8 minus R, so tangent beta equals to 2R over 8 minus 2R. Okay, so we found out the values of tangent alpha and tangent beta. So we will substitute tangent alpha and tangent beta in this equation number 1 by the values that we found for tangent alpha and tangent beta. And we will get this equation. So it is actually one equation with one variable that is R. We solve this equation, we got quadratic equation, and we have two solutions for this quadratic equation. The first solution is R equals to 6 plus 2 times root 5, and the second solution is that R equals to 6 minus 2 times root 5. But because of the fact that the side of a square ABCD equals to 8 units, and the small circle is inside this square, the radius must be less than the size of the square, that is 8 units. So the radius must be less than 8 units. That is to say, the possibility that R equals to 6 plus 2 times root 5 that is greater than 8 units is impossible, is not correct answer, and we left only with the possibility that the radius of the small circle equals actually to 6 minus 2 times root 5, that is about 1.53 units. So we found out that the radius of this small circle equals to 6 minus 2 times root 5, that is about 1.53 units. Okay, thank you very much.